Hello everyone. Today our topic is D-metal complexes, electronic structures and properties for part 1. So I'm Dr. Abigail C. Danges from the Polytechnic University of the Philippines. And here is our discussion. The first part is the model of electronic structure of coordination complexes. So there are two kinds of methods that you would see here. The first two is the valence band theory. These methods describe bonding using hybrid orbitals and electron pairs. As an extension, and electron dot and hybrid orbital methods used for simpler molecules. Although the theory is originally proposed, it's seldom used today, the hybrid notation is still common in discussing bonding. And the second one is the angular overlap method. This is a method of estimating the relative magnitude of orbital energies in molecular orbital calculations. So here in this table, you would see the valence band theory in terms of the hybridization. So if you have coordination number 2, which is a linear arrangement based on the donor atoms, we have a hybridization of SPZ only, or SP as we describe them. Or for those that we have more than 5 or more than 6, we have the octahedral. So the hybridization would be SPXPYPZ. DZ squared, dx squared minus y squared. So for this octahedral, we have sp3d2 hybridization. For these octahedral complexes, so this is how it would look like. You have a metal center, and then we have a ligands surrounding it. So these are 6 ligands. And normally for the d orbital, you would see here the different types. We have 1, 2, 3, 4, and 5 orbitals, as you would see here. And their identification would depend on what axis they would the orbitals would be located. For example, you have your DZ here, so it lies at the z axis and also at the y-axis, okay, and so on and so forth. So we have here the crystal field theory. So this is emerged from the analysis of ultraviolet and visible spectra of the d metal ions in the solids, and applies mostly on ions in crystals, provide approximate description of the electronic energy levels, but not describe the bonding. And the last one is the ligand field theory, which is application of the molecular orbital theory, and also from the crystal field theory. This is more complete than the crystal field theory. So what about the crystal field theory? So this is a electrostatic model of simply uses the ligand electrons to create an electric field around the metal center. Ligands are considered as point charges, and there are no metal ligand covalent interaction. Concentrates on resulting splitting of the d orbitals from the group of energies, and using splitting to rationalize and correlate optical spectra, thermodynamic stability, and magnetic properties of the complexes. When a d orbital of a metal ion are placed in an octahedral field of ligand electron pairs, any electrons in these orbitals are repelled by the field, and as a result, the dx squared minus y squared and the dz squared orbitals would be at the EG symmetry as directed by the surrounding ligands and raise in the energy. And the d dzx dyz and the dxy, on the other hand, would have a T2G symmetry, which is directed between the ligands and are relatively unaffected by the field. If you would see here more closely, so you have here different ligands. The ligand would have a negative charge, while the metal will have a positive charge. So we have this called a large repulsion would be destabilized. So that will be your dxy and dyz and dxz. And we also have a small repulsion which is stabilized relative to the z squared and the x squared minus y squared. O, diba? Normally, what we do if you have a d orbitals, we would put them at the same level. So, yan yung d orbitals natin at the spherical environment. But then, if we are in the crystal field na level, it would be separated and it would have a what we call a separation of two set of orbitals. So you will see there in the line, meron tayong what we call the ligand field splitting parameters. And the separate siya, dun sa upper level would be Eg and the lower level would be T2G. So this is because the overall energy is maintained and the energy of the three T2G orbitals are lowered at the 2 over 5 and the energy level of the two Eg orbitals are raised by 3 over 5 and then you would see there na mas mataas yung energy level ni Eg compared to that of T2G. So looking into this further, so you will see this that your 3D atomic orbitals would be at the same level, but the orbital energy would be lower compared to that of the degenerate 3D atomic orbital at a spherical field. So for a spherical field, it would still be at the same level, but higher energy. And then when it comes to the crystal field, your octahedral would be separated into this. So this three would be the lower one, and the upper two would have a higher energy. A SAM book would have this representation for the orbital splitting of the crystal field. So for Housecraft, uh, they use 0.6 delta oct and negative 0.4 delta oct. But for Meissler and Tar, they use positive 0.6 delta oct for the EG and positive 0.4 delta oct for the T2G. Whether or not, very important is this, the splitting would be 2/5 and 3/5. So that is what important, regardless whether it's negative or positive. So for this one, so every book would have different representation for the splitting diagram. Application example for this one, crystal field theory, is this the absorbance of the hexa-aqua titanium 3 ion. So if you would see here in the figure, you would see there the lambda max of your ion. So if you consider this, your ion is a D1, and at the ground state, you would see that one arrow is at the T2G, and the absorption spectrum of the ion would exhibit one broad band with a lambda max of around 20,300 here. And then your lambda max is 493 nanometer. Yeah. And then this means that the absorption results from the change in electronic configuration from T2G1 EG0 to T2G0 EG1. And the value of the lambda max give a measure of your delta oct. For the systems with more than one d electron, the evaluation of the lambda max is more complicated. But for this, experimentally, it's very important for you to remember that delta ox is an experimental quantity. So delta O is a measurement which is straightforward for higher d orbitals. Energy of transition depends on the orbital energies and electron repulsion. Example here for the delta O of ML complexes are given. So for example, so chromium 3 plus would have a delta ox of 13,700 when the ligand is chlorine. And if the ligand is water, so you would expect to have a delta O of 17,400 and ammonia 21,500 and so on and so forth. So this is how you would normally would expect for a delta O for the ML6 complexes. By now, you would know that delta O would vary systematically with the identity of the ligand. And they also follow what we call the spectrochemical series, wherein the members are arranged in order of increasing energy of transition that occur when they are present in the complex. So, example here, the weak field is you have small delta O, like your halogen. This is also on high spin, and they are also pi donor. And then you have here at the middle would be your sigma donors only. And we have here pi acceptors, which would have large delta O, and it would have low spin. Okay, for the ligand field strength naman, would also depends on the identity of the central metal ions. So, for example, your manganese 2 would have a lower field strength compared to that of your platinum. So, the value of your delta O increases with the increasing oxidation state. So, oxidation state is very important. Another one is also your size. And the third one is also the metal ligand distances.